Hi there, and thanks for joining us today for our webinar about the simulation-driven optimization for advanced turbocharger design. I'd like to extend a very warm welcome on behalf of Friendship Systems and our co-organizers, Rolls-Royce Solutions, NUMECA Ingenieurbüro, and the Technical University Darmstadt. So today we're coming together for a special kind of webinar, which is more of a workshop intended to present the results that were achieved within the R&D project Gamma, an R&D project that was publicly funded by the German Federal Ministry of Economic Affairs and Energy. And I'm joined today by an excellent panel of experts, and we have great material to present. So let's get started. Let's have a look at the agenda and the presenters for today. We are going to start with an overview of said R&D project, Gamma, which will be done by Friedrich Fröhlich, also called Fritze. I'm just mentioning it, so in case you hear me calling him like that. He's a aerodynamics manager at Rolls-Royce Solutions, and myself, I'm Matthias Brenner. I'm responsible for technical sales at Friendship Systems, and I will be talking about the parametric CAD modeling of the turbocharger components within this project. And then I will be followed by Thomas Hildebrandt, CEO of NUMECA Ingenieurbüro, who will talk about the CFD workflow and the CFD simulations. And after this technical presentations about the components that were used within the project, we will have a first round of Q&A where we can discuss a few questions already. And then we will start with the next session where, first of all, Johannes Ratz, who's representing the Technical University Darmstadt here within this project, but has now found a new place at IHI. He will talk about the application case on the compressor, and next we will have Nico Lachenmeier, also from Rolls-Royce Solutions, talking about the application case on the turbocharger turbine, and then we'll go back to Fritz to wrap up everything we've seen, talk a little bit about the results and the conclusions of this project. And finally, we'll have a second round of Q&A where we can talk about a few more questions. Before we actually get started, just a few small housekeeping issues. Today's webinar will be recorded and it will be available for replay later on. You will automatically get an email with a link tomorrow, so you can watch the webinar again or share with your colleagues. If you have any questions that come up, as I mentioned, we'll have 2 Q&A sessions. You can submit them directly in the webinar interface all throughout the webinar. We'll collect these questions and we'll try to address all of them, or as many as possible, at least as time permits during our Q&A parts. And that's it from my side. So I would like to give the floor now to Fritze Fröhlich with an overview and introduction of our R&D project Gamma.
Thanks, Matthias. Can you see my screen?
Yes,
and the right one?
We can see your screen, and I'm stopping sharing my camera now so we can focus on the material now.
Okay. So also a warm welcome from my side. My name is Friedrich Fröhlich, and I had the honor to be the project lead in the Gamma project. It is a public funded project together with Friendship Systems, NUMECA, the GLR of the Technical University of Darmstadt, and Rolls-Royce Solution, former known as MTU. I will start with a brief agenda. first I will give a short motivation. After that, I will show a little bit or give an overview of what we did in this project. Then we will have a so-called deep dive into the presentations of Nico and Johannes and Thomas and Mattia. And after that, I will be back with the achievements and with some final acknowledgements. So why did we do this? What was our motivation? We started this project in 2016. When you remember to 2016, since then the world changes a lot. But in former times, so to say, we saw that efficiency or turbochargers with high efficiency are the key, or were the key to the gas genset and gas marine market. We had not only this goal of efficiency, we have also map widths and other goals and structural integrity, whatever. And all this had to fit together to give a very efficient turbocharger. We had already done at that point some successful single disciplinary optimization. But it was only one single disciplinary, so just aerodynamics or just structural dynamics. The combination of multiple disciplines in one optimization workflow was so the main goal we wanted to achieve in this project, to minimize friction losses, to get better results. And if you now look to the picture at the bottom, we see here the specification chart, or a specification chart for different applications. In dark blue, you see marine. In light blue, you see the gas marine engine, and in yellow, a gas genset. So if you have a look to that picture, you see that every engine has its own specification, its own special needs. And for example, the gas genset, you need here a very high efficiency because efficiency is fuel cost. And you need also to fulfill a very high pressure ratio to be able to place your gas genset, for example, at higher locations that are 1,000, 2,000 meters high, or to drive it in very warm condition, etc. And all those specifications, all those needs, we saw would be best addressed with multidisciplinary optimization that should be fully automated. So what did we do? I talked already about the optimizations. They will be explained in detail by Johannes Ratz later, and Nicolas Lachenmeier, my colleague, also from Rolls-Royce Solutions. We also wanted to see, or to step a little into robust design, because if you evaluate thousands of designs in a multidisciplinary optimization, this is something you would get for free, so to say. We also looked into the two-stage turbocharging, into a system of a combination of radial and axial turbine with inlet guided vanes. We investigated also the system of a centrifugal compressor with vane diffuser. especially the interactions between blades and vanes. We also calculated with NUMECA the pressure field for damping estimations. Then we had some sealing topics, bearing topics in there, which is of minor interest today. But we had, as an overall headline, we had also two demonstrators. One demonstrator is the high-efficient centrifugal compressor, and the other demonstrator is the compact two-stage turbocharging for marine applications. Okay, so far an overview about what we did in the Gamma project, and I will come back later on with the achievements.
Thank you very much for setting the scene, so to say, of this project and what was involved. Let me take over, and as I said, in terms of the agenda, I will talk a little bit about CAD modeling of the different geometries that were investigated during this project with our tool cases, and to kind of explain a little bit where this fits in. If you're not familiar, many might be. Cases is a design and optimization platform that comprises three main components. The ones in blue here, automation, that's coupling to external simulation codes, and optimization is the optimization environment where you can run optimizations and post-process results and so on. But today we will focus on the first component of cases, which is the CAD environment. And cases is basically a very specialized CAD tool with a focus on geometry variation specifically. So something that with many traditional CAD tools is rather difficult to do. We want to be able to change geometries in a very flexible and robust way during the optimization process. And for that we have this specialized environment with a focus on these things: robustness, smart parameterization of the geometry, simulation-ready geometry that can be provided directly to the next step in the process, and so on. And if we look specifically at turbomachinery design, because here within the project Gamma we're mainly talking about turbomachinery development, there we have a dedicated set of capabilities within cases specifically for turbomachinery design. There is comprehensive blade and volute modeling. You can include not only these bladed geometries or the casings, but also all kinds of other flow structures like bypasses, wastegates, cooling structures, as you see here for the axial blade, but also other parts that come upstream or downstream of your turbo machine, like ducts and things like that. So in general, cases is not only a turbo machinery tool, but a general purpose tool. So yeah, we have a very high level of customization for the development of these geometries. So there are no black box models where you can just select a certain type and enter your parameters, but you can really create everything by yourself, fully customized as a user. I mentioned this already. There is a focus on high robustness and flexibility to change the geometry, consideration of manufacturing or packaging constraints. You can analyze imported data that come from another CAD system, from a preliminary design system, or from even a geometry scan, and extract parameters from this data, or fit an existing parametric model to these imported data. Alternatively to generating a parametric model of these geometries, you can also use morphing functionality. We see it in the picture here at the lower right, where we have an imported geometry and the blades are being morphed by an RBF-based approach. And yeah, Cases also has a full scripting or programming environment, so you can also write your own customized preliminary design methods and include them in the process. This is just a quick view of the user interface to give you an idea how it looks, and yeah, just a few different turbomachinery applications. Of course, turbochargers, which is what we're talking about today, but also gas and steam turbines, propellers, fans and blowers, pumps, and hydro turbines. Okay, so much for a quick introduction, what we're using and in which environment we're doing the following steps now. And now let's come back to the R&D project Gamma and what we've done in terms of CAD modeling. Here on this picture, on our slide, you can see the different components that we worked on and that were modeled within cases. So we have on the compressor side the volute and the compressor wheel with the bladed diffuser, and on the turbine side we have the turbine wheel. The aims of the parametric models that we created here were first of all to implement the theoretical parameterizations that were provided to us within this project by MTU, or sorry, Rolls-Royce Solutions, sorry, as well as TU Darmstadt. So they came up with certain ideas and parameters that they wanted to use in the models and so on. And we basically used that as an input to implement the actual models. Of course, within the models, we also took consideration of manufacturing constraints. We'll talk a little bit more about that later on, and the experience in terms of manufacturing, but also other disciplines that was existing at Rolls-Royce Solutions. Of course, we want a high degree of flexibility in those models so that we're able to cover a large design space, as large as possible, and we want the models to be robust so that we can do a very reliable variation of the geometry within the optimization process. So let's start now with the compressor side of the turbocharger and take a look at some of the geometry characteristics. So the blade design was intended to have flank millable blade sides. That's why we use these rulings. I'll mention something more later on. And there is the option to include a curved leading edge within the blade, which would require a different type of cutter for milling. If we have a straight leading edge, then we have a completely flank millable blade. Then, as was mentioned by Fritz already, we have a vaned diffuser, which with parametric vanes, and the kind of special thing here was that the shape of these vanes can change in circumferential direction, so they don't necessarily have to be all the same. The geometry export here for CFD for the blade shape was exported in Geom Turbo format, and for structural mechanics we created a solid CAD segment that was exported in a CAD format. So if we look at the volute, we have a simple cross section which is made up of circular segments, and we had some constraints on the maximum outer radius and on the height of the volute. Regarding the meshing, we also included support structure for the blocking of a structured mesh directly within the parameterization of the geometry. I'll give some more details about this later. And we also had the option, at least, to add a portage shroud to the compressor to if it's necessary to delay the onset of surge. So let's look at the modeling process for the compressor impeller. So here we start with the meridional contours, hub and shroud contour, and then we specify the blade angle distributions or beta distributions at the hub and at the shroud. And this allows us to create the mean camber lines of the compressor profiles on hub and shroud. And we can connect these two camber lines with a camber surface. And as a next step, we specify the thickness of the profiles and at the hub and at the shroud. And then we can apply this thickness to the two camber lines we had defined before. And then we connect these two profiles at hub and shroud with these so-called rulings, which are intended to guarantee the flank millability, if that's a word, of the blade. And then we fit in between these two sides. They are extended past the leading edge, and then between these two blade sides we fit the leading edge shape. And as I said, here we see a kind of curved leading edge, which wouldn't be flank millable, but it can also be straight. And that will give us our main blade surface as well as the splitter blade, which is basically modeled in the same way as we've seen here in the process. Then as a second component on the compressor side, we have the vane diffuser. As I mentioned here, we have an individual parametric surface for each of the vanes, but they are generated in an automated loop. And we can change the parameters of the vane. We can change the the airfoil parameters in spanwise direction, height direction here. But we can also change the shape of these vanes in circumferential direction to possibly take into account asymmetries or in the flow that are due to the volute being non-axisymmetric and things like that. And the inputs are either distribution functions for certain parameter values, which basically describe how a certain parameter of the vane changes in circumferential direction, which will then give us differently shaped vanes. Or, of course, these values can also be constant, and then at least that parameter is the same for all the vanes. And finally, the last component on the compressor side, the volute. As I mentioned before, we have a cross-section here that is modeled with circular segments. You can see it here on the right side. And the main kind of parameters that are being changed here are the so-called board angle. You can see in the very in the bottom left in the animation, you can see the change of this board angle. And we can also change the distribution of the A/R ratio in the circumference of the volute. So if you're not familiar, A is the cross-sectional area, which is highlighted in gray here, and R is the centroid radius of this area. And as you see here in the diagram, we can set up a distribution function that describe how this A/R ratio changes when going around the volute scroll. As I mentioned, we have some space constraints regarding the maximum radius and the height. So you can see in the animation here in the middle, if we reach the constraint for the maximum radius, the cross section, if we increase the area, starts growing in vertical direction, and basically we hit the constraint and stop there and then grow in vertical direction. And if we reach the maximum height, which is the other constraint, then the cross section starts moving inward, or starts growing inward, basically. The very critical area in the volute is the so-called tongue, or cutwater, or whatever you want to call it, where the scroll basically self-intersects itself or intersects the outlet diffuser, and that tongue is modeled with a custom fillet surface, which has the advantages of having a very good and clean representation, being very robust when we change the shape of the volute, as you can see here in the animation. And having a very good quality of the overall solid that we export, because obviously for meshing and so on later on, we don't want to have open edges or intersecting faces and so on. That would kind of throw stones in our meshing process. And then within the parametric model for the volute, we have included some preparation for the meshing process. It's actually for geometries like these volutes, it's quite difficult to create a robust structured meshing, especially when we're changing the shape very flexibly. And the idea here was that we create a support geometry for the blocking of the structured mesh directly within cases inside of the parametric model. So basically the support geometry is coupled to our geometry directly, and if we change the geometry, we also can adjust these block boundaries very nicely, and then we can export the boundary curves to IGG for the meshing process, which we'll hear more about from NUMECA. And that's about the meshing. And finally, on the compressor side, we had 59 parameters that were used for optimization purposes, which basically are related to the shape of a hub and shroud contour, obviously blade parameters that control the blade shape, and as well as the diffuser vane, the impeller back as well that we don't see here, which is maybe not aerodynamically interesting, but for structural reasons, and of course the shape of the volute. So if we move over to the turbine side and look at some of the characteristics of the geometry that we developed there. So we have so-called radially fibered blades, which means that all points on the blade camber surface are dependent on the hub streamline. So as you can see in the picture, we have our hub camber line on the hub, and then basically going from the axis of rotation, if we extend radially outward through our hub camber line, we obtain the camber surface. And that's structurally beneficial because basically it aligns the fiber of the blade with the centrifugal forces. Exactly, that's what I was looking for. And so it's structurally beneficial, but it's also beneficial in terms of the optimization because the shape of the blade is mainly controlled by the hub streamline, and then it reduces the number of design variables of the model. We can see also here with the cross sections, airfoil sections applied to the blade, how it looks. There is also the possibility to add some end wall contouring to the hub, which means that or is obtained by changing the hub contour. So if we have our meridional contour for the hub, rather than having a constant contour that is just revolved around the axis of rotation, if we change that in circumferential direction, we can get this contouring on our hub, and that's can be aerodynamically beneficial to influence the flow and maybe secondary flow phenomena at the root of the blades, but it's also beneficial in terms of reducing inertia, so we can take off some material there, and then of course we want to have a turbine with as low inertia as possible so that it revs up quickly and shows a good dynamic behavior. And for the same reason, we can also add these scallops or webbings to the hub. In terms of structural integrity, the fillets at the roots of the blades are also quite important, and it's actually, I mean, not very surprisingly beneficial when the fillet radius between the blades or at the bottom of the blades is as large as possible. And here we had included in the model an automated routine that basically calculates the maximum fillet radius automatically using an internal optimization, and then gives us the result that we want. And in terms of the export, we want to export, again, simulation domains for fluid calculations and structural computations, and they have to fit exactly to each other, so they are also generated directly from within the CAD model and exported. And as we've heard, we also were looking into combinations of axial and radial turbines, and maybe as a side note, also this model or the parameterization was constructed so that within the same model, within the same parameterization, we can also generate the axial variant of the turbine, so to say. So let's look at the blade modeling process for the turbine side. We again start by generating the meridional contours, hub and shroud, as well as the back disc contour. Then we generate the camber surface by creating a hub camber line. This is described here as a theta over m prime distribution. So theta is the rep angle, and we describe how the rep angle is distributed, and this gives us our camber line on the hub. And then, as I explained before, starting from the axis of rotation, we extend the radial fibers through this hub camber line and generate the camber surface. And then we want to apply our thickness, blade thickness, and for that we have a parametrized cross section that is controlled by a few points along the curve, and then we have values for the width position of these points in radial direction. So you can see, if you look at these parameter distribution graphs, you see obviously we start with high values for thickness at their inner radius, and then we get thinner, and some of those points converge to the same value, so that we just have a constant thickness, and this will give us the blade surface. On the turbine side, we had a total within the model of 70 design variables, and 40 of those were selected for the optimization process. All right, that's it from my side about the CAD parametrization. Now I would like to give over to Thomas Hildebrand from NUMECA, who will tell us a bit more about the CFD setup, CFD workflow that was used here. Let me make you the presenter, Thomas, and the floor is yours.
Matthias, many thanks. So give me a second. Okay. Can my presentation be seen? I take that for yes. So very good afternoon, everybody.
Yes, it can.
Thanks, Matthias. Matthias just set the stage for my talk. So we were a member of the Gamma team, and we consider that a very successful project and a very nice collaboration in the team. So what I'm going to show you today is the optimization workflow for the turbine, for turbocharger design from the meshing and CFD simulation side. Okay, good. So in the first part, I cover the workflow, how we try to stitch all the parts together. Then how do we set up such a CFD simulation in order to make it really robust over a wide range of operating points and parameters. And at the end, I have a few words on the structural mechanics meshing. Good. Okay. The optimization workflow. So the goal here is to have a fully automated, multidisciplinary and multi-point optimization workflow. So that can be quite challenging. So mainly because of the range of the parameters can be really vast, and also the multi-point is a tricky part. So we have to cover a whole range of operating points. So in order to make that a stable and reliable workflow, we need a very robust geometry and grid generation for the whole design space. So Matthias just covered the geometry generation, and the grid generation was our part. We also need a very high mesh quality in order to guarantee reliable simulations and also reliable convergence behavior. The CFD simulation setup sounds trivial, but again, here you have to take into account the wide range of operating points and a lot of what if this and that happens. And all that has to be coupled in an automated way, covering different softwares. Okay. Also interesting in case that you have to foresee a case where an actually aerodynamically good design can be rejected because of meshing or geometry issues. And in that case, we don't want to lose that promising design. We are going to redirect the optimization into a more stable direction. Good. The optimization workflow. The part you're seeing here has just been covered by Matthias. So cases delivers us geometry for the volute and for the impeller and diffuser. I cover that in more detail later. What we do before we start, what we do inside the optimization, the first thing is to mesh the structural part. So the CSM stands for computational structural mechanics. So we mesh the solid body and calculate and simulate that the structural stresses via calculix, and then we go into the CFD. The reason for that order is quite simple. The CSM calculation takes a fraction of the time of the CFD calculation. So if a design fails mechanically, we put that into the database in order to maintain the information of a fault design. But we don't run the CFD simulation. The flow result of a design which is structurally not integer is basically worthless. Good. Then we, in case of two successful simulations from the structural side and from the fluid side, we take the CFD and CSM result into the optimization loop. We use in that case an artificial neural network in a genetic algorithm. So we have an adaptive response surface, we get an optimized design, we feed that into the database, we modify the parameter back into CADIS, and the whole loop starts all over again. Okay, the proof is in the pudding, how to couple different softwares. So we have on the geometry generation side from CASIS, CASIS delivers us an impeller with splitter blades, plus the diffuser, and plus a volute. So this is on the fluid side. And additionally, we get an impeller section, the impeller solid body for the structural side. We couple that via parasolid files and Jom Turbo files. Jom Turbo is a native NUMECA input file for the meshing. And we also need additional curves, in particular for the volute and meshing template. This is what we're going to provide in order to turn that geometry into a mesh. Then we mesh the different parts, the CFD part, the structural part, and the volute. All has been done by different philosophies, and we stitch all that together to a workable mesh. Good. Let's cover that section about CFD meshing and simulation. Before we set up the optimization, what we do first is manually meshing the first parameterized design. Manual meshing is not an option inside optimization, that's obvious. But for the first shot, we optimize the mesh manually, have a close look, and quite important, we take a grid convergence study in order to find a good compromise between a good, solid CFD simulation and an acceptable mesh size. So since we are running hundreds of design, it's basic, every mesh point counts, I would say. So we try to minimize the overall mesh size and still maintaining a good accuracy. Part 3 is just a simple sentence, automation of volute meshing, but it was really, I would say, a major part of that project to make a volute, to mesh a volute automatically, robust over the whole design space in a structured way. I come to that later. And at the end, we run robustness tests for the geometry and the mesh generation. A robustness test means we're just generating hundreds of meshes over the whole range of possible parameters, possible parameter combinations, and we check whether the mesh is still a good mesh after even very strange parameter inputs. So that's important to guarantee a high rate of success, however the geometry looks like. Technically, we mesh the impeller and the diffuser. We have a multi-row mesh. We use one passage for the impeller. We use a 360-degree mesh for the diffuser, and the volute is also meshed completely, obviously, and then we stitch that together. Now have a look in, let's look into that in more detail. CASIS delivers us the impeller plus a vane diffuser in a parametric geometry generation. We export that as a Jom Turbo. This is a native NUMECA AutoGrid input file. It's a simple ASCII file, very clear. We're going into AutoGrid 5, which is NUMECA's block structured meshing tool for turbo machinery components. And we run the mesh generation in batch mode. We use so-called templates. A template is a model describing the mesh parameters in the sense that we specify how many points we have on the pressure side, how many points we have on the suction side, in the tip gap, blade to blade, and so on. So working via templates guarantees us that all the meshes are of similar quality and of similar quantity. So this is one thing you can do very nicely with structured meshes. Finally, we export that mesh. You see here, this is the compressor impeller, the impeller plus a diffuser. So it's a multi-stage mesh. We incorporate the tip gap. We have blunt trailing edges in case of the impeller. And we also take the real geometry of the bulb, meshing down to radius 0 into account, and also the blade fillets here around this splitter blades and main blades. We did not do that here, but seal leakage and cavity flows can also be taken into account. Okay, now let's come to the volute. Very early on in the project, we decided to use a block-structured hexahedral mesh for the volute. So many people would say this is a hell of a work, and they are right. It was quite some work, but we deliberately decided for going for structured mesh in order to guarantee a high mesh quality and also to have a very fast solver speed. So typically, if running a structured solver can be about 3 times faster than running an unstructured solver, and we wanted to take that into to take that advantage here in the optimization. So the decision was for block structured hexahedral mesh. The challenge is the tongue region. So the rest of the volute is basically just a bended tube, so that is fairly easy to do. But where the tube is matching the other tube, that can be quite tricky. This is so-called tongue, and here you have really to think hard about how topology to use. Okay, here's a close-up look, and you can already see the block structure is quite interesting. And it was, as I said, quite a challenge to make such a block structure robust over a whole range of geometry variations. Good. How does a block structure look like in detail? We used 2 rings, an inner ring, the red one, and an outer ring which wraps around the inner ring and closes into itself. And then we have a transition block here. And this is the main topology we're using. There are much more details in the real world, but in the frame of that talk, that should be enough here. This is a close-up of the mesh. It's not the mesh we use, so the real mesh is quite a bit finer, but it should give you a flavor about the block structure. Important was, as you see here, quite a number of curves. So these are additional curves we use for the stabilization of the meshing process. And here a very close interaction with cases came into play. So cases delivered us these curves, also in a very parametric robust way, which we have to use for that purpose inside the optimization. There was a lot of fine-tuning involved, of course, and these curves has been exported in parasolid format into our mesh. Okay, so this is how a volute does look like in cases, and we took these curves, these supporting curves for our meshing process, incorporated in our meshing tool IGG and started meshing. Good. So the entire meshing process here was script-based. Again, it's a Python script which reads in the cases curves and surfaces and starts our meshing process. Export came from Parasolid into IGG, which is our manual mesh generator, which we did not run in a manual way, but in a script controlled way here. And then the blocking started, as you can see here. And the next point was the optimization of the grid point distribution. And finally, we mapped the final mesh here onto the final geometry. You see here, there's this discrepancy between the geometry and the mesh. We use the conformal mapping to put the mesh exactly on the surface. So out comes a meshed volute. And finally, we put all that together. So the volute, impeller, and diffuser is a close-up. And you see a beautifully structured mesh of a complete turbocharger impeller. Good. So far for the meshing. How was it CFD set up? So here's the mesh. And we went into, put the mesh into Fine Turbo, which is our turbo machinery specific solver. It's probably the fastest turbo solver on the market. It's a structured solver. It has a very high quality and reliability. And I think the simulation time we have here is really competitive compared to unstructured CFD solvers. Again, full batching and scripting capability is important inside an optimization process. So here's a numerical setup. As I said, we have the full volute naturally, we have the full diffuser, and we used one passage of the impeller. Before we started, we made different studies on turbulence models, inlet-outlet boundary conditions, interfaces. So a lot of variables we had to play with before we went into the big optimization. Again, robustness tests were here a topic as well. We used for steady state simulation, we used total pressure in the inlet here. We used in the outlet around the design point and stall point, we used mass flow, and the choke point, we use static pressure. So this is the beautiful mesh boiled down to the numerical setup. You see here the solid surfaces. The red part is a rotor-stator interface. This is the diffuser blade. And here we have what we call a full non-matching boundary condition, where we connect the diffuser to the volute. Good. If you run a multi-point optimization, you naturally have to run multi-operating points. And there are several ways to do it. So we have the design point, choke point, and the stall point. You can run all 3 points simultaneously on a number of processes, which in total speeds up your computational time. On the other hand, starting an operating point very close to the stall can be a bit tricky. So we decided in most of the cases, we decided to take the design point as an initial solution. And from then we went to the stall point and the choke point. In case a steady state simulation is not enough for the optimization, we considered only steady state. But for a detailed look into the flow, we were interested in the unsteady solution. We used the nonlinear harmonic method. The nonlinear harmonic method is a quasi-unsteady method. I try to explain that in a nutshell soon. It gives you mostly an improved time mean flow solution. Even if you don't look into the unsteady results, your time mean flow is improved quite a lot. The continuity across the rotor-stator interface improves by using the nonlinear harmonic method. And we have no restrictions on the number of blades and blade rows. Computationally, only one blade passage is taken into account, but that can be periodically multiplied. So how does the nonlinear harmonic method works? Traditionally, if you use a classical time-stepping approach, you have the full model. So that's what we call a 360-degree model. So you have to mesh the full impeller and the full diffuser, and then you step the impeller in tiny steps until you have completed a couple of revolutions. So this gives you big meshes and many time steps. So what people try to, when people try to take a shortcut, they find common integers between the impeller pitch and the diffuser pitch, and multiplying the pitches a bit and then stretching them. So that works basically the same way as a full model, but with a reduced mesh. But here, your frequencies are not longer the same because you play with the blade pitches. So we're using a nonlinear harmonic method, taking only one blade passage into account for the impeller and one for the diffuser. We use here a Fourier decomposition. We're considering transforming the Navier-Stokes equations into the frequency space. Time-wise, the speed up is very considerable. Today, a run simulation takes a couple of hours, depending on your mesh size and number of processors. The nonlinear harmonic method is about, let's say, typically 10 times, takes 10 times more time than a Reynolds, the classical run simulation, but we are still in the range of hours, while a full unsteady simulation, we are close to days and even weeks. A validation of the results. So this is a snapshot of a full unsteady simulation of our impeller. You see here that's an entropy plot, entropy leaving the impeller, entering the diffuser. And here we use a nonlinear harmonic with 3 and 12 harmonics. You can see the differences between a classical unsteady simulation and non-linear harmonic simulation are negligible, but there's a factor of 50 in the computational time. Good. The final part here is the solid body mesh. How did we mesh the structural part? Again, cases delivered as the geometry, a fully parametric periodic segment of that impeller plus splitter blades. You see that here. So slice through the cake, and the CSN solver Calculix we use accepts only tetrahedral elements. So our measure delivered a hex dominant mesh. So we have to take something. We have to do something for that. There were quite a number of requirements. So we had to use more than one cell per blade thickness for accuracy reasons. The leading edge and the fillet capturing should be as exact as possible. And we need to have a matching periodic connection on both sides. We use the surface to volume approach in hex plus hybrid, which is our unstructured measure. We got the geometry segment out of Parasolid, and we used what we call a configuration file with a number of keywords, also specifying the main parameters on the mesh. Good. So from cases, we get the parametric model. It's being exported as Parasolid. Hex plus hybrid first creates a hex dominant mesh with a periodic matching connections. You see here that's mainly a hex mesh. And in the next part, we are splitting that hex mesh into a TED mesh. And then we export that into Calculix. The features, as I mentioned before, so you see here we have a fairly accurate capturing of the fillets. We have between 2 and 3 elements over the blade thickness, and also a quite good approximation of representation of the leading edge here. And the mesh was periodic matching. So finally, we got what we wanted, impeller segment consisting only of TEDs with all the quality requirements we imposed on the structural mesh. So that was the entire optimization workflow, starting with the geometry generation to the CFD meshing and simulation, the structure meshing and all that put together into the optimizer, and finally leading to a better design. So that was my talk. Thanks a lot, and I'm looking forward to the Q&A.
Thank you very much, Thomas. And yes, we have now time for a little bit of Q&A. Let's say we will continue with the next presentations in about 5 minutes from now. So in case someone doesn't need to hear the Q&A and needs to get a coffee or something like that, then feel free to come back in 5 minutes, and if you want to see the remaining presentations. I have some questions here, maybe a first one that I can directly address, which is related to the radially fibered keyword. Actually here someone was asking about radially fibered meshing does not result in a bad mesh at the tips or a skewed mesh. Maybe let me clarify that. So we're not talking about the radially fibered meshing, but we are talking about the radially fibered geometry. So it's the way the blade is generated, which, as I explained, means that we align the camber surface of the blade in the direction of the centrifugal forces, so that we have better strength with regard to these forces, but it's not related to the meshing of the blade or the meshing of around the blade. So there is no issue there with the mesh that in some way results from the radially fibered construction. Um, we have a question here to Mr. Hildebrand specifically. For the geometry optimization, will NUMECA communicate and invoke cases to reconstruct the geometry, or will it work on curves inside NUMECA? I could also answer something, but maybe you'll take it. And then
No.
there's a follow-up question, maybe about the optimization process. How are the parameters filtered with regard to non-significant parameters versus more significant parameters for the optimization results?
Okay, let's start with number one. We are using cases as the geometry generator inside the optimization. So we have own geometry generators, but in that case, because of the flexibility and also the volume generation, cases was addressed by Fine Design 3D, which is our optimizer, in order to change the parameters. Number two is about filtering insignificant results.
Right, or parameters. Basically, I think it's more something related to do you take a look at the sensitivity of the objective with regard to different parameters, and do you maybe exclude some parameters that are not so significant versus
we're doing that. So we run a sensitivity study and also an ANOVA analysis. And you can clearly see the impact of several parameters. The downside is, not the downside, but it's inherent in the process, that you have to run quite a number of shots in order to get a sensitivity already. Right. So in the beginning, yes, you include insignificant parameters, which you can exclude later. That's possible.
Yeah, definitely makes sense. Thank you. There is a quick question that I can address, which is related to modeling overlapping fillets at the turbine blades. So actually, this was a situation. In principle, of course, you can also model overlapping fillets. There were some issues with the robustness of the geometry when we get fillets that overlap each other for neighboring blades. That's why here we integrated this process of making sure that the fillets do not intersect. So we have a very robust setup, and we get the maximum that we can get without intersecting. I don't know if there are other issues. This was one specific issue other issues that might be related to that. But yes. And there is maybe final question before we continue with the other presentations, which is related to surface roughness. Maybe this is something that our colleagues here from Rolls-Royce Solutions might be able to say something about. What is the impact of surface roughness, e.g. to compare additive manufacturing versus a machined surface? Is this something you have any experience with or could say something about?
The surface roughness of machined impeller for the compressor, so I can say it for the compressor side at least, is for sure better than a printed compressor. Yeah. Mm-hmm. But we didn't in the calculations we didn't take into account surface roughness because for our machines it was not of any significance.
Do you have any kind of experience with additive manufacturing created impellers? If it might have an influence because it's a rougher surface and maybe it's not so good, or is this not something that you have tried so far, let's say, or? measured, at least so far?
This is a question perhaps Nico can better answer, because he's nearer to this 3D printing topic.
Yes, maybe I can say something to that. So on the turbine side, we have some experience with different manufacturing methods. So we have the fine casting process that we usually use in a series production, but in the prototyping phase, we use also different manufacturing processes, such as a milling process or additive manufacturing process. Mm-hmm. And it looks a lot like for our turbine sizes, the different surface roughnesses don't play a vital role. It might be different for smaller turbines, I guess, maybe for automotive turbines, but the roughness is very, very small compared to the overall size of the turbine, and we didn't find or measure significant difference between different manufacturing techniques up to this point.
All right. Yeah, thank you. Very, very good. Thank you for these answers. So let's finish this Q&A session and continue with our agenda, so that we were able to cover everything that we need in the time that we have. So I would like now to invite our next presenter, which is Johannes Ratz from IHI now, Technical University Darmstadt at the time of the project, and he will tell us something about the optimization of the compressor side of the turbocharger. So let me make you the presenter. Oh, sorry, that was wrong. The floor is yours.
Hopefully everyone can see my presentation.
Yes.
Welcome to simultaneous multidisciplinary optimization of compressor, vent diffuser, and volute. First of all, I want to give you a short introduction, mainly to those people who are not too deep into the topic of turbochargers and centrifugal compressor optimization. Then I want to show you the optimization workflow. Many things are already said by Mattia and Thomas about the geometry creation and CFD and CSM setup. So I will make it short, but repeat some stuff which I think is important. And finally show the results of 3 optimizations I've done. So first, in general, to the topic, what is a turbocharger? A turbocharger is a part of an engine. Here you can see an engine by Rolls-Royce Power Systems. And the turbocharger mainly consists of a turbine and a centrifugal compressor. So the turbine on the left side is later considered by Nico, and my part now is the optimization here on that centrifugal compressor. So we are optimizing the geometry of that impeller, diffuser, in my case, it's a vent diffuser, and the volute, so the spiral housing around the compressor. And the main task of that compressor is to increase the pressure with a sleeve to the engine, to the combustion chamber. So such a compressor is mainly characterized by a performance map. So it's the total pressure ratio dependent on the reduced mass flow. And you can draw those lines here on the normalized rotational speed. So we know, like, for a certain rotational speed at a certain reduced mass flow, we get a certain total pressure ratio. And that certain total pressure ratio, we get to a certain efficiency. And one objective which is quite clear is increase the efficiency. So the better the efficiency in the overall performance map is, the better the efficiency of the whole engine is. But there's another objective we need to consider, and to understand why we need to consider that is, if an engine accelerates, the turbocharger is accelerated along such full-load curve. And if we want to accelerate an engine even faster, that full-load full load curve is shifted to smaller mass flows. So the problem is that we have something like surge limit. So if the surge limit is crossed, at least, normally the turbocharger is damaged or maybe completely destroyed. So the second objective we need to consider during such an optimization is to broaden the performance map, so to shift the surge limit to lower mass flows so that the full load curve is completely inside our performance map. So now we have our two objectives we want to consider during our optimization: increase the efficiency and increase the performance map width. The problem is with a pure aerodynamic optimization, we often get a poor structural integrity. So besides our CFD, we need to carry out a CSM, so a computational structured mechanic analysis, to be able to evaluate the von Mises stresses and the eigenfrequency of the impeller. Yeah, so far to that small introduction, what we want to do or what we want to optimize. Now I want to show you our optimization workflow. You already know that picture from Thomas. So we have one optimizer. It's a framework. It can be Fine Design 3D. It can be Cases or Mode Frontier. And that framework, the optimizer is placed. So we using a genetic optimizer, a multi-objective genetic optimizer, combined with meter surfaces to optimize the geometries. And those optimizers modifying the geometry parameters. And then, as Matthias mentioned, Cases is getting those parameters, and based on that geometry parameters, Cases creates the geometry. So the volute, the impeller, and the diffuser. And after creating the geometry, we're going to the CFD meshing and simulation, to the CFM meshing and simulation, afterwards giving the results back to the optimizer, and the optimizer starts the next round with modified parameters. So let's start with Cases. So Matthias showed many possibilities. I only showed the possibilities which are important for exactly that optimization I show later on in the results. So for that optimization, we changed the complete impeller geometry, the diffuser geometry, and the volume geometry. So we did a simultaneous optimization of all three parts. Starting with the parameterization of the impeller, we're defining the hub and shroud contour, the leading and trailing edge in a meridional plane, adding a better angle distribution at hub and shroud, and the definition in the meridional plane plus the better angle distribution transformed to a three-dimensional room gives us our 3D camber surface, as Matthias explained a little bit in more detail. Adding to that 3D camber surface thickness distribution, we now get our final 3D plate. And their main plate and splitter plate is mainly modeled the same. So what we are doing is like we're giving a better angle distribution for the main plate at hub and shroud. And we're using that better angle distribution for the splitter plate, adding small variations. So the splitter plate mainly follows the main plate, but can change the better angles along the camber surface a little bit in both directions. So as I said, we not only want to create a domain for the CFD calculation, we as well need to define the impeller back to mesh the solid body to calculate the structural mechanics. And for that, we're changing the length of the impeller, we're changing an angle here at the back, and what's quite important is the length here of the back. So it's very important to influence the stresses in the rear part, which are often too high. Getting to volute, maybe one parameter I haven't mentioned before is the clocking position of the diffuser. So we are not only varying the plate camber of the diffuser, but as well the complete rotation, the clocking position, so we can we can change the impact of the flow which is hitting the volute ton. Going to the volume parameterization itself, it's mainly parameterized by the A to R ratio and the board winkle. So having a look here at that cross-section, the A to R ratio is defined by that area of the cross-section divided by the radius from the center of that cross-section to the rotational axis. The overhang value mainly is that angle here, which makes it possible to move the volute a little bit more out or in. So both values, like the overhang or board angle, as well as the A to R ratio, are varied around the circumferential direction, so from 0 to 360 degrees. The board angle is parameterized as a linear function, whereas the A to R ratio is parameterized by 4 values, so it's not only changed by a linear function, but rather a logarithmic shape will be or would be possible whatever values we choosing for the deviation at the beginning and the end of that line. And finally, we get here a quite nice value for later CFD calculation. So finally, we have a parameterization for hub and shroud, main and splitter plate, diffuser plate, impeller back, and volute. And that optimization I show now had 56 free parameters. So now after our geometry generation, we're going to the meshing of the CFD. So you already know that pictures. We have a fully automated meshing process within AutoGL AutoGrid 5. The impeller plate is a single mesh. The diffuser mesh is full 360 degree. And we are including the fillets. The volute as well is automated block structured within IGG, and those messages are then combined in AutoGrid 5 with the 3D effect. It's quite nice because then later on during the CFD process we can use the turbomachinery initial solution. So for those who are a little bit involved into NUMECA, or in general in CFD, it's sometimes quite hard to get a start solution for geometry, and that turbomachinery initial solution guesses the pressure inside the whole geometry, so the start for the CFD is more smooth, and the CFD is more likely to converge. We are going to CSM meshing, so we implemented 2 ways. One is the way Thomas showed. Another way is with Simlet from Altair. I have a short talk again about the hex-plus hybrid method. So first we are creating a hex dominant mesh using then the data mapper to transfer the hex dominant mesh to TED4 elements, using then the open source to Gmesh to transform the TED4 elements to TED10 elements. And that's very, very important. Like in the first step, we only use those TED4 elements, and to get a mesh independent solution, for that case, we need a really, really fine mesh. But using that TED10 element mesh, the mesh can be much more coarsened to get the same results. And finally, that's a small problem maybe from Gmesh, or for us at least, it was a problem. The Gmesh format is not executable with Calculix, so we had to write a small Python script which transforms the Gmesh format into the Calculix input format. So then we could finally calculate that mesh with Calculix. Yeah, so now where we have our geometry and our meshes, we can go to the simulation, starting with the CFD simulation on the left side. That's our domain. So we have a single passage for the impeller using periodic boundary conditions, then having a mixing plane interface before going into the 360 degree mesh diffuser, and then a full matching boundary condition to go into the volute. we calculated 3 operating points, or considered 3 operating points during the optimization process. So 1 to evaluate the choke limit, 1 to increase the efficiency in the design point, and 1 highly throttle point to have an idea about the performance map width. So with these 3 with these 3 operating points, we can define our 2 objectives, the isentropic efficiency and the performance map width. And we have our 2 constraints, the total pressure ratio and the choke mass flow. Going to the DSM calculation, Calculix gives us the first plate eigenfrequency and the max mesostresses at the main plate, the splitter plate, the fillets, the bottom, and the trill. So the constraints are the first plate eigenfrequency have to be higher than a certain level, and the von mesostresses need to be lower a certain level. Yeah, so that's the optimization workflow. So with that optimization workflow, we carried out 3 optimizations. What you can see here is a plotting the 2 objective functions against each other. So on the y-axis, you see the efficiency. It's the first objective function. On the x-axis, you see the performance map width, or in that case, I called it estimated surge margin. And all the designs you see inside that plot are one valid design. So in total, we carried out 1,400 valid designs. A valid design means that CSM and CFD calculation converged so that you can evaluate the aerodynamic and the structural values from that calculations. So the first optimization we carried out where the optimization where impeller, diffuser, and volute was changed at the same time. The second optimization, which is based on the first one, we changed a little bit the parameterization of the diffuser. And in the third optimization, which is based on optimization 2, we changed the diffuser from a standard diffuser to a low solidity diffuser with the aim to increase the surge margin. So what you can see as well is a quite nice Pareto front, but all the designs down here do not fulfill all the constraints. In that area, mainly the total pressure ratio constraint is not fulfilled, or the choke margin constraint is not fulfilled. So those designs are valid, but not feasible. So the feasible designs you can see up here in that rectangular. So feasible design means, or a feasible design is a valid design which fulfills all the constraints we set. And on the right side, now you can see all our feasible designs. So those designs are all fulfilling our constraints like total pressure ratio, choke margin, and structural constraints. So from that Pareto front, you can see up here in the right corner, we decided us for 3 designs. One design with a quite high efficiency, one design with a medium efficiency and a medium surge margin, and one design with a lower efficiency but a high surge margin. Compared to the baseline design, so the values are normalized, so the baseline designs is here at 1,1. So compared to our baseline design, all 3 designs have an improved efficiency and an improved surge margin. Maybe one additional information comparing optimization 2 to optimization 3. So that design was that design. It's the same impeller, but the diffuser changed radically. So the plates are much shorter, and here we have 19 plates against 13 plates for low solidity design. Here, first of all, I have a direct comparison between the CFD and the experimental results. On the left side, you see total pressure ratio. On the right side, the efficiency. Gray, the baseline design is plotted. Orange, the optimized design with a medium efficiency and medium surge margin. And the dashed lines with a triangle are the experimental data. So between numerical and experimental data, we have a very good agreement. For total pressure ratio and efficiency, And even for that design, the surge margin is met quite well between experiment and CFD. So comparing the optimized design to baseline design, we have a little lower total pressure ratio, which is mainly the reason because our total pressure constraint was reduced compared to the baseline design, and we're getting for the design point a 1.4 percentage point higher efficiency. Having now a look at the design with the highest efficiency of the optimization, again, the overall agreement between CFD and experiment is quite good, except of the surge margin. So the CFD shows a higher surge margin than the experiment. So in that case, the CFD overpredicts it. But regarding the efficiency, the agreement is very good. And compared to the baseline design, we have a 2.28 percentage point higher efficiency. And if we have a look at the overall value, so we have an efficiency over 87%, which is really, really good for that design size. Yeah, the last design, the low solidity design, has the lowest efficiency, but the broadest performance method. So we only have a 0.48 percentage point higher efficiency, but a much larger performance method compared to the baseline design. And in that case, the agreement between CFD and experiment is a little better, but in that case, the experiment overpredicts the surge limit compared to the CFD, whereas in the other design, the CFD overpredicts the surge margin against the experiment. Maybe one more helpful slide before we had a direct comparison for only one design. Now we are comparing trends. So we're plotting all the designs in one chart. On the left side, the total pressure ratio for the CFD calculations. On the right side, the total pressure ratio for the experimental data. And what we can see here is that the total pressure ratio, or the level of total pressure ratio, is really good for between CFD and experiment. The choke margin trend is met really good, but what's the problem is the surge margin again. The surge margin predicted by the CFD is, not the same, but quite equal for all three designs, whereas this experiment shows a much larger surge margin for the low solidity design compared to the other burst designs. In the end, that was our aim, to increase the surge margin, but the CFD didn't predict such a large increase in it. Regarding the CFD, the same comparison, are the trends correct or not? Having a look at the lower and the medium speed line, the trends are really good. So the low solidity diffuser has the lowest efficiency, then the medium efficiency design comes before the high efficiency design. Only for the highest speed line, there we have some problems. So the experiment shows a higher efficiency for the low solidity design than the CFD. That's probably due to a separation inside the diffuser, which is not correctly predicted by the CFD. So maybe having a short look why the total pressure ratio is lower and the efficiency higher between the designs. So what we can see here is the difference in total pressure ratio and the difference in the efficiency compared to the baseline design along the full compressor. So compressor plane 1 is the inlet into the impeller, 2 is the outlet of the impeller, 3 is the inlet to the diffuser, 4 is the outlet of the diffuser plates, 5 is the inlet into the volute, and 7 is the outlet of the volute. So we can see where the single designs are increased in pressure or have lower pressures compared to the baseline design. The same for the efficiency. So having a look at the total pressure, we can see that the total pressure loss or the total pressure rise is lower for the optimized design. That's mainly based on that the impeller plate exit angle is lower, but in the rest, so after the impeller trailing edge, the total pressure loss is smaller than for the baseline design. Having a look at the efficiency, we can see that the efficiency increases over the whole flow path except of the volute. So we already have an efficiency increase in the impeller and the even larger efficiency increase in the diffuser compared to the baseline design. Why is that in the impeller? So without digging too much into the flow structure here, the main reason for the higher efficiency in the impeller is the positioning of the splitter plate. So what we can see here are the entropy plots for different meridional positions inside the impellers. And you see here that in the channel of the splitter plate, the entropy production is much higher in the baseline case than for the two optimized designs. And yeah, having a look at the plate loading, you can see here that for the optimized designs, the plate loading is quite equal here in green and orange between splitter plate and main plate. But for the baseline design, the plate loading here in dashed lines for the splitter plate is much higher than for the main plate. So the secondary flows are much increased, which finally lead to a much stronger jet wake area, which finally leads to a 0.5 percentage points higher efficiency for the optimized designs. Yeah, having a look at the diffuser, yeah, the efficiency difference is even higher. So the main reason why the efficiency improvement could be fulfilled with the optimized designs is that for the baseline design, so here you see the diffuser plate of the baseline design, leading edge, trailing edge, inflow direction. The problem is a large separation bubble at the hub. And that separation bubble you can see here by means of the mass flow rate at the plate-to-plate cut at 10% span. That separation bubble is suppressed by the optimized designs. Yeah, that's the main reason why we have the efficiency increase in impeller and diffuser. So to finally conclude those optimizations or in general our work, we created an optimization workflow for multidisciplinary optimization based on software packages from Friendship Systems and NUMECA. We carried out a simultaneous optimization of impeller, diffuser, and volute, and finally reached a 2 percentage points higher efficiency improvement, an absolute isentropic efficiency larger than 87%, and the low solidity design has a surge margin from almost 30%. Yeah, thank you for your attention, and I give it back to Matthias.
Thank you very much, Johannes, for this quite interesting presentation. Especially I liked your detailed analysis of the results and the reasons why certain results might be better or different than others, which we don't see that often. So it's quite nice. So let's go over to the next presentation, which will look at the application of the optimization workflow on the turbine side. So I would like to give over to Nico Lachenmeier from Rolls-Royce Solutions for his presentation. The floor is yours, Nico.
Thank you, Matthias. I hope you can see my screen.
Yes.
Okay, perfect. So I will talk a little bit about the radial turbine optimization that we conducted within the research project Gamma, and how we did that using the parameterized geometry model that Matthias introduced earlier this afternoon. So I have a few slides prepared. I'll start with the motivation and objective, then I'll talk a little bit about the optimization workflow and the optimization results. And at last, I'll come to a short summary and an outlook and talk about where we intend to go with all this work and workflows. Okay, motivation and objective. Yeah, as we've heard before in Johannes' presentation, the turbochargers that we develop are for these large engines that we see here. It's either diesel or gas engines, and the turbocharger system essentially shapes the dynamics, the fuel consumption or the emissions of the engine in general. This is why we have a very keen look on the turbine and the compressor. We just saw how Johannes worked on the compressor, and it was my job to design the turbine. And well, what is the turbine supposed to do? Obviously, it has to deliver enough power, because the turbine is supposed to drive the compressor. It has to be efficient. It usually has to be as lightweight as possible, and it has to fulfill certain lifetime requirements. That is, of course, a very general way of looking at a radial turbine. When it comes to the actual design, we find that it's very application dependent, whether or not, say, efficiency or inertia is very important or not. We sketched that here on the right. So you can see that for different applications, we usually have a different focus. And of course, the workflow that we developed should be, of course, able to take all this into account. And well, this is then what we try to do. So when we started Gamma, our main goal was to do some what we call analytical front loading. So when we design a new turbo machine, a new turbine, we want to know as much as possible about the turbine as early as possible, and that is only possible if we have a full parameterization of the model, and with that we can judge the turbine performance as soon as possible by means of simulation. And well, our goal was to create more efficient turbo machinery with comparable mechanical properties. So our requirement for the Gamma project was to get a complete geometry parameterization and build up an automated meshing and an automated simulation workflow that is then put into an optimization workflow in order to improve the turbine. Which brings me to the optimization workflow, starting with the geometry parameterization. We saw that now in detail in Matthias' presentation, and some of it was repeated in Thomas and Johannes' presentation, so I'll keep it short. The three important steps to model a blade are as follows. We usually start with creating a meridional view. We see that on the top right in black. This is what we do first. In a second step, we define a camber distribution. This could, for example, look like this on the bottom. This yellow greenish line here is describing the theta distribution from inlet to outlet. And in a third step, we describe and define the thickness of the blade with, of course, different thickness distributions at hub and at shroud. And we also created several parameters to guide the thickness distribution from hub to shroud. So it's not necessarily linear, but we can have, say, an S-like shape, for example. As we've seen also before, the model features some nice add-ins. For example, we can model scallops, which is very important for us. We can control the fillets in a very detailed manner. And of course, we can change a lot of stuff that usually is not discussed when it comes to optimization. For example, we have full control of the back of the turbine, and the front of the turbine, of course, can be controlled as well. Having this geometry, we can create a model that we see here on the left that is then used for the mechanical calculations, and we create a model that is then used for the CFD calculations. Having these models, we need to create meshes. We create several meshes dependent on what we want to do with them. For example, when it comes to the cost functions mass, center of gravity, and inertia, all we need is a surface mesh. So it's enough to have, say, a tessellation of the turbine surface, and with that, we can calculate the mass and the center of gravity. Those two cost functions are important to constrain, because if the turbine gets too heavy or the center of gravity is pushed too far away from the bearings, we might get rotordynamic issues. And of course, we also look at the inertia, which is important in terms of the acceleration behavior of the turbocharger, but it's also important with regard to the bursting energy of the turbine. So we have to prepare for the case that the turbine fails for whatever reason, or the turbocharger fails, and then the turbine might burst, and that burst energy is proportional to its inertia, and we need to contain that energy. This is why we would like the inertia to be as low as possible. Just like on the compressor side, we also look at the stresses. We usually do that by looking at the stress at different locations individually. So we control, say, the maximum stress in the fillets, the maximum stress in the turbine back and say the maximum stress in the scalloped area, for example. And we control all these stresses individually and try to keep them below a, say, specified threshold. We usually also look at the eigenfrequencies of the blade. It is common practice to constrain the first blade mode to lie above a specified engine order. And sometimes in case we design turbines with inlet guide vanes, we have an even deeper look at eigenfrequencies and look at higher eigenfrequencies as well. And last but not least, of course, we do a CFD calculation, which we then use to, of course, determine the efficiency of the turbine, but also make a first estimate of how big the volute will be in order to make a first judgment of the size of the whole turbine, including the volute. Having automated all this, we can do an optimization. Usually we try to keep the parameters, the free parameters in the optimization as low as possible. Usually we have something like 30 to 40 parameters in an optimization, which is still quite a lot, which means that we need to consider a lot of designs during the process. The design, however, the parameterized model has much more free parameters. So I think the whole model has about 70 parameters. We just simply don't consider all of them during optimization, trying to keep the optimization effort as low as possible. The optimization algorithm that we use is a genetic algorithm. It's meta model assistant. So the optimizer tests several meta models, such as, for example, radial basis functions or neural networks, and picks a specific meta model for each cost function that is considered, and checks that every now and then if it's still the best one, and sometimes even does a switch during an optimization. As I've said, we need to consider a lot of designs, which is why such an optimization process can take quite a while. Usually in my experience, it's more than 3 weeks, even considering that we have actually a lot of high performance computing power available. It just needs time, and usually it's not like you press the play button and wait for 3 weeks, but instead it's usually more like you run it for a few days and then you see that you have to change the optimization setting, or that you, I don't know, have to change parameter bounds, and then you restart the optimization with the database that you already have. So it's an off and on again procedure usually that, in my experience, takes me 3 to 4 weeks until I say, okay, we have arrived at a suitable design that I then discuss with the mechanics team. Of course, we did not only create prototypes, but digital prototypes, but also actual hardware. Some of the results I'm going to show here. So what we see here is a radial turbine that is supposed to be the low pressure stage of a 2-stage charging system. And of course, I'm not allowed to show actual efficiencies, but you have an idea of how the turbine works if you look at this efficiency plot here. The green lines are a turbine that we basically had in stock, a classical radial turbine that was developed by hand several years ago, and the blue lines show the efficiencies for the turbine that we see on the right. We see we gained in efficiency, but we also see that we improved the turbine in terms of its mass, its moment of inertia, and its center of gravity, which is shown by the numbers here. By the way, this is actually, I think, a 3D printed turbine, and as you can see, there is a little bit of surface roughness, but it's in the same range, I'd say, as the casted models. We did not only create the low pressure stage, but also the high pressure stage. So this is a turbine that is supposed to run at pressure ratios in the range of 1.3 to 1.5. And as you can see, this is also where this turbine has its peak efficiency. Sorry, I missed to translate the slides here. So this is supposed to say efficiency, and this is pressure ratio. The green lines show the efficiency of this new, let's call it axial turbine, or you can also call it mixed flow turbine if you like. And in blue, we find the efficiencies of a radial turbine. The problem is that at Rolls-Royce, we do not have other axial turbines that we could compare this one to. So I simply chose a radial turbine that has a comparable reduced mass flow and compared then the efficiencies. Again, we see that the turbine is doing exactly what we want. So it's perfectly suited to a two-stage turbocharging system. And what the turbine also has is that it's very lightweight. So we reduced the inertia by 20% and its mass by 27%. So it's our assumption that the acceleration behavior of this high pressure stage should be very good. As we have hardware, we can of course also conduct measurements, and this worked out very well. So on top we see the reduced mass flow. The straight lines are what we calculated using CFD, and all the dots are results that we gathered from our test benches. So we find that, well, our predictions are well met in terms of the reduced mass flow. On the bottom, we see efficiencies. Here, the matter is much more complicated because in CFD, we can only calculate adiabatic isentropic efficiencies, whereas determining the same efficiencies at the test bench is very tricky, if not impossible, which is why one usually just looks at the so-called total turbine efficiency, which also includes mechanical losses of the bearings, which is why the two efficiencies, stated CFD and the measured efficiency, are hard to compare. Nonetheless, it's well within the range that we expected. What we did in Gamma as well is that we tested two different bearing concepts. Usually, Rolls-Royce turbochargers are equipped with cheap journal bearings. Ball bearings yield a higher efficiency, a higher turbine efficiency, but are also more expensive. We tested it here, and of course, what we see here is that we improve the total turbine efficiency drastically and can create further benefit in the range where this turbine is going to be driven, so around the pressure ratios of about 1.5. Of course, the benefit is not as high for high pressure ratios, but that's not where we intend to operate this turbine. Okay, this brings me to my last few slides, to the summary and the outlook. But first, I would like to talk a little bit about the practical parts of turbine design. So on the left, I tried to sketch the development process, how it used to be when I joined the Rolls-Royce company. I joined the aerodynamics team 7 years ago, and back then when we designed a turbine, it worked like this. I proposed a blade design. I gave the blade design to the solid mechanics team. they usually found that it's insufficient. So usually the stresses are too high or the eigenfrequencies are too low. And then they give me that feedback, and then I go again, try to find a new blade design, and we played ping pong, say, for a few weeks until we finally found a design where we were both happy with. And with that design, we went to the CAD design department. They created the full annulus model that then again went back to the solid mechanics team and was judged by them again, and also back to the aerodynamics team. So we burned a lot of time in this traditional process, just pushing geometries back and forth. And this is something that drastically changed now with this new way of working, just because we now have a fully parameterized CAD model of the whole turbine that is fed into an optimization algorithm together with all the requirements that come from the different departments, from the aerodynamics team, from the solid mechanics team, and also from the CAD design team, who usually just say define maximal diameters or maximal lengths or stuff like that. And feeding all these requirements, we can start an optimization, and we get a design that, in my experience, is really, really close to the serial design. There are usually minor changes that have to be made, but it's not like overthrowing the whole design. And with this adjusted design process, we save a lot of time. Which brings me to my summary. So as we intended, we were capable of doing an analytical front loading. The digital prototypes are available as early as possible, and the designs that we create have improved drastically. Within the project Gamma, we designed 2 turbines, a low pressure and a high pressure stage of a 2-staged system. And once again, I missed to translate a letter. So the maps that we calculated via CFD were confirmed by the measurements. And of course, we do not intend to stop here. So we're still working on extending the whole workflow. For example, one of our aims is that we want to include full lifetime calculations. The problematic part about lifetime calculations is that you need reasonable temperature distributions within the turbine to calculate lifetime. And what we also want to include, we started with that, but it's still a very costly process to calculate the burst energy during a natural burst of the turbine. The expensive part here is that we have to include plastic deformation in the CSM part, which makes the calculation expensive. And finally, we are also putting a lot of work into not using a gradient-free workflow as discussed and shown here, but we intend to use gradient-based methods in the future. In particular, we want to exploit adjoint methods to accelerate the process even further and to avoid the curse of dimensionality. So thank you for your attention, and please feel free to ask questions.
Thank you very much, Nico, for this great presentation. It's always good if you get to see some photos of real objects every once in a while, especially in the work that we're doing here at Friendship Systems. We see a lot of 3D models and CFD pictures, but sometimes it's good to see a real object. So yeah, we've looked at the optimization workflows on compressor turbine side, and now I would like to give the presentation to Friedrich Fröhlich for final wrap-up results and conclusions. Please, the floor is yours.
Yeah, thank you, Mattia. So the Gamma project, as you saw, helped us to provide perfectly tailored turbochargers to our future engines and fuel cells. One of the core parts was fully automated, multidisciplinary, multi-objective optimization. Those optimizations helped us a lot to improve the level for the goals we wanted to optimize. You see here at the right bottom, you see a sketch where I want to show this. So we had here the level in blue of efficiency before we started Gamma and after Gamma. So we increased the efficiency for a turbocharger of the same size at around 4% points here. Therefore, you need an extremely stable and flexible geometry generation like it is provided by cases, and also, as Thomas already told, very fast CFD solvers so that you can calculate a lot of designs. And therefore, it has to be, in my opinion, it has to be block structured. And as I saw from now, I found it worth the time looking to that block structured volute because it's really a nice feature, and I love it to work with it. So those two things, I think, are the basement of every good optimization workflow. I brought you some demonstrator designs we optimized with this, and I show here efficiencies because I want to tell you, want to show you how good this worked out at the end. We saw here low pressure compressor. I have also the high pressure compressor, both with very high levels of efficiencies. I'm not allowed to tell the diameters of those wheels, but you see this really works out. How did these results help us in a quick changing environment like today? So when we started this project 2016, it was so to say different times. Yeah, we were going, or we are currently going through a pandemic, through a disruptive change of our climate. So all influences that came very sudden, very quick, and we had to react on it. And how does this help us? So at first, we raised the level of efficiencies of our turbocharging for the gas engines, for the diesel engines, for the fuel cells. That saves itself. This itself saves CO2. High efficient turbochargers are, so to say, the entrance, the door to a lot of H2 based technologies like the H2 engine or the fuel cell. So this would not be possible with a normal, so to say, normal turbocharger. We also, as Nico already pointed out, we saw a speed up in development timeframes. So it is working quicker, and we don't need so much loops for a design. We also saw a speed up in time resolved CFD, for example, for the damping estimation. We need pressure fields, we need transient pressure fields, and we really saw this speed up with NLH. Okay, so thanks a lot to the team. Yeah, thanks a lot to Friendship Systems for the geometry generation, for the Karun-Löwe expansion, NUMECA for the CFD and optimization software, for the fully automated structured volute meshing, which was really a big step, I think. I really like this feature. We have the unstructured solid meshing and the uncertainty quantification. Thanks also to Johannes Ratz and the GLR from Darmstadt University for the optimization workflow for the centrifugal compressor and the high efficiency compressor they designed. So I also want to say or give my acknowledgements. This project has been funded by the BMWI. Thanks for funding and support to Mr. Benjamin Hamacher and Dr. Busse Gerstengaber and their team. It was very helpful, their advice, and they guided us through this funding process. Thank you for that. Okay, so I hand back to Matthias.
Great. Thank you very much, Fritze, for these clear conclusions. It was obviously a pleasure also for Friendship Systems to work on this project. I think we have learned quite a lot in the field of turbomachinery design, which also helped us improve the level of service that we can provide, but also the tools that we provide to our customers. And yeah, it was really fruitful collaboration. So we are nominally at the end of the time that we had allocated for today's webinar, but I think we can take a few more minutes to answer some of the questions that have come in before we wrap up completely. I have a question here which is related to optimization methods. I don't know who's the right person to answer it. It might go equally to Johannes as well as to Nico. The question is, have you compared alternative optimization methods? For example, gradient-based method might be much faster or orders of magnitude faster than genetic algorithms. Yeah, do you have any experience with that for these kind of projects that you have worked on?
I guess that's the right question for Nico.
I think so too. The answer is yes. At least at Rolls-Royce, we're trying to get the gradient-based methods started. We are trying to get the joint-based methods started. But and I second that it's much faster, orders of magnitude faster. I fully agree on that. But it's also orders of magnitude much more complicated in setting up. So building up a workflow like this is, in my humble view, a much easier task than building up a joint-based workflow that is also CAD-based at the end. So it's much more tricky, but we're working on it because of exactly this advantage that it's supposed to be much faster.
Yeah, that makes sense. Maybe one question that's from my side, just as a follow-up to that. Obviously, for example, something like a genetic optimization is a very global method that allows you to cover a lot of ground in terms of design space. Of course, it takes more time. How about that in comparison to a gradient-based method, which per se initially is a much more local optimization? Do you see a big difference, or are you able to get at the end to similar results?
That's a very difficult question because you would need to run a lot of optimizations to get an answer to that.
Yeah.
I personally, I just know one publication that actually tried to compare gradient-based and gradient-free methods, and they came to the conclusion that they can find exactly the same results. They found the same turbines at the end. However, the gradient-based workflow was much faster, so there was no problem with any local minima or stuff that is usually brought up when it comes to gradient-based methods. So they didn't encounter these problems. But then again, it's just one example. It's not a proof.
Yeah.
But, well, it could be a disadvantage, I agree, but it hasn't been proven that it actually is in the context of, say, radial turbines.
All right. Yeah, that's fine. Thank you. Just one question here is about, how easy it was for MTU or Rolls-Royce Solutions maybe to adjust the workflow and the parametric models to new applications? Is it something that you already are able to say something about? Can you? I mean, we've seen the application of the workflow on these specific components. Is it easy to transfer it to new applications, like, I don't know, a turbocharger for a H2 engine or a compressor for a fuel cell or things like that?
Okay, Fritze, you want to answer?
Yeah.
Or?
Okay. Yeah, I can at least answer this for the compressor workflow. It is not done within 10 minutes or so, but yeah, you can easily adapt it. So it is, but if the more precise you define your goals, your objective functions, and your boundaries in the beginning, the better the result is. Yeah, and therefore you need a certain time. But this workflow, in terms of workflow we got from Friendship and NUMECA, like geometry generation, meshing, CFD stuff, yeah, this is really easy to adapt.
Mm-hmm. Very good, thanks. Yeah, there's a question here for NUMECA, I think. Is it possible to use the nonlinear harmonic method also within the optimization workflow?
Yes, absolutely. This is one of the beauties of the nonlinear harmonic method. Input-wise and from the entire setup, it behaves like a stationary steady-state simulation. You enter the number of harmonics, and that's it. And you converge the Navier-Stokes equations for the different harmonic frequencies like steady-state equations. So it's no difference to the standard runs we're doing. The unsteadiness happens at the reconstruction later on in post-processing. So yes, we did that. Okay.
Thank you. And final question that I think I can answer that is related to the number of parameters of the geometry. So we've seen in these application cases that we had a rather large number of parameters, things like 40, 50, up to 70 parameters, which of course is a massive load for optimization. And there is a question regarding how that can be reasonably reduced in order to run the optimization in a reasonable time frame. And I think I just want to pick up something that Fritze showed in his thank you slide in his presentation, which was called Kahun-Löwe expansion for Friendship Systems. This is also something we've worked on in this project that wasn't shown here, which is a methodology to reduce the dimensionality of the design space. So basically, if you have a parametric model with a large number of parameters, then typically you have certain correlations between these parameters. So maybe different parameters might influence the same areas of the geometry, and there is a mathematical method to remove these correlations basically, and transfer the parametric model from one parameter space into a new parameter space where you have parameters that are uncorrelated. And this is a very interesting method. We have used it on some application cases here within the Gamma project. It is available also in cases, and we're doing currently in kind of a beta stage, and we're doing currently more application testing to see where it is well applicable and how kind of the best practices are to apply this method. But if it works fine, it can really reduce the number of parameters quite massively from maybe something like 30, 40 parameters to just a handful of parameters while retaining most of the variability of the model. And yeah, it's quite nice. All right, so I think that's all the time we have for today. We've covered the questions that have come in here. We've shown a lot of interesting material. Thank you very much to my panel of co-hosts and co-presenters today. Thank you very much to the audience for attending this webinar or workshop. We hope to see you or hear from you in another situation. Of course, if you want to deepen the discussion about any of these topics with us, feel free to reach out to any one of us about that specific topic. And again, thank you for joining us today. Stay safe, stay healthy, and yeah, see you soon, hopefully. Bye-bye.
Thanks, Matthias. Bye-bye.
Bye-bye.
Bye-bye, everybody.
Bye.
Thanks to Matthias for moderation.
You're welcome. Thank you.